Good morning, good afternoon, and good evening. Thank you for joining Bazel Day on Google Open Source Live. This is a monthly series of sessions led by open source experts from Google and community leaders. We really appreciate everyone taking the time to come here together digitally to learn more about Bazel. My name is Joe Hicks, and I'm a product manager here at Google, and I'm based in the New York City. I'm also here with Sylvia.
Hi, folks. My name is Sylvia Isler, also known as Sylvia Isler1 on Twitter. I'm an engineering manager here at Google. I'm located in New York as well.
We have some really interesting topics for you all today. If you're looking to learn more about Bazel, you're in the right place. We'll kick it off with a talk from Doug Parker, walking us through how he migrated 2,500 apps to Angular Ivy, which is really a case study on Bazel transitions. Before that, we have a couple housekeeping items.
Don't forget to put your questions in the live Q&A forum below the live stream window. Speakers are ready to answer your questions live. If you're viewing in full screen, you'll need to exit full screen to see the live Q&A forum. Our sessions have been pre-recorded to allow for accurate transcripts and so that speakers can answer your questions live. We would love to hear your thoughts on these sessions, so feel free to make comments in the live forum, and we'll check them throughout the show. Once we're done, don't forget to join us at the after party on Google Meet. We'll share a link at the end of the last session. And one last thing, use the hashtag GoogleOSLive to share your experience on social channel. Anything else, Joe?
With that, enjoy.
Hello Bazelers, my name's Doug and I'm here to talk to you today about how we're migrating over 2,500 applications to Angular Ivy using Bazel transitions. I'll be telling you what the Ivy migration is, why it's so tricky, what Bazel transitions are, and how we're able to leverage them to scale this migration safely to so many applications. My name is Doug Parker. I'm a software engineer at Google, specifically on the Angular team. If you're not familiar with it, Angular is an open source framework for building high-quality web applications, and I definitely recommend you check that out if you build web apps. Not only do we have support for Bazel, but we even use Bazel in our core GitHub repository, where external open source developers contribute their code to Angular. So we really love Bazel on the Angular team. But today I'm here to talk to you about a Google 3 migration. Google 3 is the mono repository which stores most of Google's internal source code. It's a massive Bazel workspace with millions of lines of code, and we want to upgrade it to Angular Ivy. Ivy itself is a new version of our rendering engine recently released by the Angular team. The specifics of it aren't too important for this talk, but it's a smaller, faster, and just generally better than our old system. It also makes puppies and kittens happy, so we're really pushing applications to use it. We've got over 2,500 Angular applications in Google 3, so we want to upgrade them to Ivy as quickly and easily as possible. Fortunately, Ivy itself is a reimplementation of existing Angular APIs, which means that applications generally shouldn't have to change their code in order to work with Ivy, making a migration much simpler since turning on Ivy is as simple as a flag flip. So if all we want to do is flip a flag, then this should be an easy change, right? Well, let's see how this might work. In Angular, we have our own build rule for compiling code. ngModule is our equivalent of TS library, Java library, or whatever your preferred language's library rule is. It's just our version. Ivy itself is a compiler flag, so it needs to be provided to the compiler action that runs under the ngModule rule. This means that the easiest way of enabling Ivy is to simply add it to our ngModule starlark implementation, passing it as --ivy equals true to our compiler actions arguments. Since we're working in a monorepo and we only have one version of ngModule, if I merge this change, then all applications will immediately build with Ivy. That's incredibly easy, and it's also incredibly terrifying, for one simple reason that's best described by Hiram's law. Hiram's law, if you're not familiar with it, it essentially states that if a system has a sufficient number of dependents, then eventually all observable behaviors of that system will eventually be depended upon by somebody. And while Ivy is theoretically backwards compatible, it is a reimplementation of these existing APIs. There are subtle differences in them that were never officially in the API contract, but applications have nonetheless managed to depend upon. With thousands of Angular applications, enabling Ivy would inevitably break somebody, no matter how backwards compatible we try to make it. If we enable this globally, as I showed a moment ago, then when one application has a production issue, we'll have to roll it back for everyone. And that can cause outages, increase friction for developers, negatively impact users, and it makes puppies and kittens sad, so we need to reevaluate our rollout strategy. Rather than roll out as one giant flag flip, we want to roll out incrementally. Specifically, applications should be able to opt into Ivy individually. Enabling Ivy for one application should not affect any other applications in the workspace. The Angular team should still control the default value, because with thousands of applications, asking them to migrate individually wastes a lot of time for everyone. We want to be able to just migrate those applications for them, hopefully without them even noticing. Even if this makes my job 100 times harder, it stops thousands of other teams from doing the same work, so it's still a huge win for the company. In order to safely flip this default value, though, we need to be able to opt out any applications that would be broken by Ivy. By doing so, we're able to safely enable Ivy by default for the vast majority of applications without causing any breakages. We'll also need a rollback strategy. If someone encounters a production outage when we flip this default value, they should be able to roll themselves back without affecting any other Angular application. There's also one other unique constraint that this brings up. Angular Ivy was originally developed with the expectation that an application is either entirely built with Ivy or not at all built with Ivy. You can't mix part of the application compiled with Ivy and part of it compiled without Ivy. That just doesn't work at runtime, and it's not the way the system was designed. What this means is that our builds need to be consistent. Either the entire application builds with Ivy or none of it does. And if you're experienced in Bazel, you might be thinking about how you could implement this rollout. So let's look at a couple approaches that immediately come to mind. Firstly, Bazel provides --define in order to specify custom build flags, where developers can add --define, some flag name, and then the value, and you can read this at build time in starlark. We could use one of these to implement Ivy. The tricky part here is that developers must always provide this flag manually, so you have to remember to add it at the end of every Bazel build command. I don't know about you, but I can't remember to check the test pass before I send a PR for review, so I'm definitely not going to remember to do this. Alternatively, we could add this flag to our Bazel RC configuration file, so it's automatically applied on every build. That at least saves me from embarrassing myself in front of my coworkers. However, this also means that it applies to all applications in the workspace, so we can't apply this flag on an application-by-application basis like we really want to. The problem here is that these flags apply to the entire compilation, which is just too broad for our purposes. We want this to be application-specific, so this just doesn't quite work for us. Another way of implementing this flag would be to simply make it an attribute on the ng module rule. We can propagate this attribute to the compiler action and invoke that action with ivy. This could be a little awkward, as we'd have to put ivy equals true on all of our ng module rules, and that could be a lot. But we could automate this or use a clever macro. We could make that scale if we really needed to. So this actually sounds pretty good, but let's look a little bit closer. Let's say, as an example, we have a workspace with two applications. Each of those have a couple targets, and both of them depend on Angular core. Core is our standard library core functionality. And for our purposes, everything depends on core, because if it didn't, then it wouldn't be an Angular app and we wouldn't care to migrate it. So we can just pretend everything depends on core. Each of these boxes is a different Bazel target, and they're all ng module rules. So each one has its own invocation of the Angular compiler and its own version of the ivy flag. Since we're rolling out incrementally, we only want to change one application to use ivy, and the other one should just be left alone. We can compile app1 as ivy, but then leave app2 without it. But this immediately brings up a tricky problem, which is how do we compile Angular core? Since it's just a regular ng module, there's nothing special about it. If we enable ivy, then app1 will work, but app2 will break. And if we disable ivy, then app1 fails, but app2 works. So we're really stuck between a rock and a hard place here. This is that shared library requirement in action. A library can be used by multiple applications using different values for ivy, and the library needs to somehow be compatible with both of these. But that's just not how the compilation works. What we really need are two different builds of Angular core, one that uses ivy and one that doesn't. There are a few ways you can sort of make this work. You could split Angular core into two targets via some kind of clever macro and make sure that all of these applications depend on the correct version. This actually becomes quite difficult for a number of reasons. For instance, keeping your dependency edges consistent between the two applications can actually be quite tricky. And not to mention, in your actual source code, if you're importing things referenced by the file name would then be changed, and so all your imports would be wrong, and you'd have to update those. So this actually becomes quite tricky very quickly. Ultimately, the problem here is that we're opting out individual targets, which is just too specific. It's kind of the opposite problem from what we had earlier, and it just doesn't support shared libraries in the way that we need to. So how do we want this to work? What I want to do is add ivy equals true to the top level application target, just modifying it in one place because I'm a bit lazy. Then, when we Bazel build the first app, it should compile everything with ivy for itself and all of its transitive dependencies, including Angular core. However, when I Bazel build the second app, that should compile everything without ivy, again for itself and all of its transitive dependencies. The lesson here is really that Angular core doesn't care whether it's built with ivy or not. It's happy to build with ivy if that's what the application wants, and it's happy not to build with ivy if the application doesn't. But is this kind of design actually possible with Bazel? You may be surprised to learn that the answer is actually yes. This is done with Bazel Configurations and Transitions, which are the way in which we're able to configure builds to provide this kind of functionality. First, I want to explain some rough definitions. Every target gets built with a configuration, and you can think of a configuration as the set of compile time flags and their values. Every target has a configuration which contains all of the flag values that target can read when it's executing its rule. Transitions are the means of transitioning the build graph from one configuration to another. This allows you to modify flags for a particular set of targets, effectively changing those flags dynamically based on the build graph. A target's configuration gets inherited by all of its transitive dependencies. This means that transitioning even a single target to a new configuration will also apply to that target's entire transitive dependencies. Those dependencies will also use the new flag values that were changed by the transition, and this is a really powerful feature which we'll be taking full advantage of for Ivy. So hopefully that gives you some rough idea of what these terms mean at an abstract level. So let's look at something a little more concrete to help clarify these concepts. First, let's consider a simple build graph that has three targets depending on each other. Each target has its own configuration and the set of flags that it compiles with. In this case, they are all using the default configuration, meaning that they use the default values for all of their flags. In particular, the test flag uses the default value of hello for all targets in this graph. We can introduce a transition to the bar target, which will transition its flag value from hello to world. What this means is that when bar executes its rule, it will see the test flag now has the value world. This transition has effectively changed the value of this flag for bar. Baz will also see the value world because it inherits this configuration from its parent. This means that all transitive dependencies of bar will see the new value of world. Foo, on the other hand, is unaffected, and it continues to compile with hello because it's sort of above all of this in the build graph. Now, that's a lot of high-level concepts, so how might we be able to apply this to solve our problems with Ivy? So let's revisit the original design we came up with a moment ago and how we can use transitions to implement it. We can add a new attribute called Ivy to ng module and set it on app1 binary, the top-level target for that application. This will enable a transition which sets the Ivy flag on the configuration. This means that when we build app1, Ivy is transitively inherited for all targets in an application, as well as any shared libraries like Angular Core. When we build app2 binary, on the other hand, it is left alone because it did not set the Ivy attribute. So it does not have a transition, and app2 continues to build using the default value of false passed all the way down to Angular Core and builds correctly without Ivy. With this architecture, we're able to use transitions to isolate these applications from each other, while still using the correct Ivy flag for each application, even for libraries shared between the two. We're also working at the right level of abstraction now. We're opting in applications rather than individual targets like earlier, so this is much closer to what we originally wanted. By now you're probably sick and tired of box diagrams, so let's take a look at some of the actual code we would use to implement this. We start by defining a simple flag. We load this from Skylib, which is a library that has a lot of great Bazel utilities, flags being one of them. We pick some build file to define this flag, and we simply add bool flag as a rule. Since this is a simple build file, it actually has a target. This one exists at //angular:/Ivy flag. It's a little strange that it sort of has a position in the build graph and you can depend upon it, but that's actually how we're going to use it here. So now that we have this flag, we need to update our ng module rule in order to depend on this Ivy flag. Because Bazel is Bazel, we need to explicitly declare all of our dependencies, and that does include flags. In this case, we're creating a new attribute which depends on this flag by default. This essentially means that all ng module rules will now implicitly depend on this new flag. Finally, it's time to actually read this flag's value. In our rules implementation, we can use the context object to find the Ivy flag attribute that we just declared and read its value as a simple Boolean. For now, I'm just going to print it out with the target's name, but you can certainly imagine passing this flag to your compiler as an argument, or even choosing between two completely different actions. Maybe you want to have one action specifically for Ivy code and another action that invokes a separate compiler for non-Ivy code. And that's entirely possible with this design. Finally, when I'm able to build any ng module rule, this code will execute and it will print out the flag. For now, building app1 binary shows that it and all of its transitive dependencies are built with Ivy set to false. So we successfully read the default value of this flag. Now we need to set it via transition. Now what we want to be able to do is add Ivy attribute equals true to the top level ng module rule and trust that all of its transitive dependencies will build with Ivy. We shouldn't need to add Ivy equals true to all ng module rules because in a real app that'd be a lot, and frankly I just can't be bothered with it. Now I'm calling this one Ivy attribute. That's just to distinguish it from the Ivy flag that we defined earlier. It's just to drive home that these are two completely distinct Boolean values that are going to be working together to create the behavior that we want. We start by declaring an Ivy attribute defined as a simple Boolean and defaulting to false. This is because we expect applications to opt into Ivy. This works just like any other attribute you would use on a rule, and if you've done rules in Bazel before, you've done this countless times, and there's nothing special here. Now we get on to the actual meat and potatoes of this, the actual transition. We use the transition function in order to create a new transition, much like the rule or aspect functions if you've used those before. We need an implementation function that I'll show you in a moment, which will perform our actual business logic for this transition. We also need a list of input flags and a list of output flags. Because again, Bazel is Bazel, we need to explicitly declare our dependencies on everything. You thought we were going to get away with it for once, but that's just not the case here. The inputs are the flags that we want to read into our transition, while the outputs are flags that we want to write to from our transition. In this case, we want to read and write the same Ivy flag, so that's the only one here. For the actual implementation, we define a new function that was referenced in the implementation parameter earlier. This function receives two parameters. First, it gets a settings dictionary, which contains the input configuration flags which we declared as inputs mapped to their current values. In this case, it would be a dictionary with the Angular Ivy flag mapped to whatever its value in the configuration that we inherited. This is essentially whatever the inherited value for Ivy flag is. We also get an attributes object, which contains all of the attributes of the current target, such as name, deps, and most importantly, the id attribute. For the actual implementation, we start by checking if the user provided id attribute. And if so, we want to change the id flag and set it to true. In order to do that, we return the new configuration in the same format as the settings object. In this case, we just set / Angular id flag to true. Now, if id attribute is not set, we simply pass through or propagate the input configuration with no changes. This is essentially saying, just use the same configuration as my parent, I don't want to change anything. So transition logic is actually really simple, and all it does is read flag values and return new values. This whole talk is on transitions, and yet the actual code fits on one slide. I am lying a little bit. There's one more thing we need to do, which is that we need to simply add this to any affected rules. In this case, we need to update ng module and say that its configuration sets to the transition that we just created. This will execute the transition for all ng module rules. So now let's try it out. In order to switch an application to Ivy, all we need to do is add Ivy attribute equals true to its top level ng module. Then when we build this application, we'll see that the binary, the library, and most importantly, Angular core, all successfully built with Ivy. All of these targets are in agreement about the Ivy flag. They will all build the same, and they'll be able to work together at runtime. Separately, if I build an entirely distinct application, like app2, which does not set Ivy, then we'll find that its binary, its library, and even Angular core are all built without Ivy. Again, they're all in agreement, and they're all able to build correctly and work together at runtime. So let's back up a little bit and review what we were originally trying to accomplish. We wanted to be able to opt in applications individually, and we've successfully done that by enabling Ivy for app 1, but by leaving app 2 alone. The Angular team also still controls Ivy attribute, and we can manipulate its default value. We can easily switch its default to true and make everybody build with Ivy when we're ready. Similarly, we can opt out broken applications by having them just explicitly pass Ivy attribute equals false, and they will be protected from the change in default value. We can also leverage this as a rollback strategy. When the default changes, everyone moves to Ivy, but if one application finds a production outage, then they can simply add Ivy attribute equals false, and it will roll them back without affecting anybody else. The other 2,500 applications still successfully roll out with Ivy. And in both cases, we're able to be consistent. Either everything is Ivy or nothing is, and we've successfully solved that shared library problem from earlier. So where are we right now? As of the time of recording, we have about 27 applications which have launched Ivy to production using our transition infrastructure. Currently, we're resolving a few of the remaining blockers and hoping to enable Ivy by default soon. One day, you may soon see that all your favorite Google Angular applications are suddenly running much smaller and faster, and all of this is enabled with the magical powers of Bazel transitions. So I hope this was informative and interesting, and I look forward to seeing what the rest of the Bazel community can do with transitions. Thanks for watching.
Well, thanks, Doug. I'm super impressed with the power of Bazel to help Angular with their difficult problems migrating to Ivy. Also today, we have folks joining from across the globe. I want to shout out to folks from Canada, Germany, Belize, and everyone connecting from Asia. It's pretty late there. Thanks for joining. Fun fact about Belize, you can get rice and beans at every restaurant, no matter what else they serve. And in Belgium, it's critical that beer be served in the proper glass so that it was designed specifically for, so as to ensure the best tasting beer. There's not many questions in the live Q&A yet, so feel free to add some or ask questions of the speakers. Next, we'll hear from Lukasz Berkey about Bazel for Android open source platform. Take it away, Lukasz.
Hello there, I'm Lukács Berki, the tech lead of the Bazel build tool. Today I would like to talk to you about one of the more significant projects, which is to build Android platform with Bazel. That is to say, not individual Android applications. We can already do that, but the operating system itself. First, I would like to talk to you a bit about the history and why we are doing this. Then I would like to talk to you about the difficulties there are. And then I would like to talk to you about what exactly is happening and what accomplishments there are. History. Long and storied. I would like to not dwell too much on the individual items on this slide. What is important is that both the internal monorepo and both Android platform have a story that's almost 2 decades old. Both of them started out from Make, and since then they have diverged. Our internal monorepo is using the internal version of Bazel called Blaze. Android is currently using a version of a bespoke build tool called Sung and still bits of Make. So why build Android platform with Bazel? There are multiple reasons, both organizational and technical. The organizational reasons are simpler, which is to have one single solution to the same problem and not two. This decade and a half of parallel development resulted in different solutions to the same problems, and developers do find it hard to move from one world to the other. I speak from experience. I spent a whole lot of time in our internal monorepo, and then when I started working on Android, it took me quite a bit of time to learn all the separate tools. And it's better for other developers not to have the same experience or the opposite of it. The technical benefits are also many. First off, we do provide a way to execute build actions remotely, which is important because Android is a big operating system, and one of the biggest complaints there are is that builds are slow. Distributing the build over multiple computers helps with that. Bazel also provides a sandbox for individual actions, which is important for incrementality. That is to say, this is how Bazel makes sure that when an input file is changed, only those actions are rerun that are actually affected by the change. Nothing more and nothing less. This creates trust in the build tool because, as anyone has ever said, make clean knows that when this happens, when incorrect incremental builds happen, that can give rise to hours and hours of wasted time of debugging. Bazel also provides a number of tools to look at the structure of the build. For example, to look at the structure of the action graph, that is to say, the graph that is composed by the actions and their input and their output files, and the individual targets, for example, C++ or Java binaries or libraries. Last but not least, Bazel has a vibrant community, both inside and outside Google, which is useful for one to get started with building Android. Of course, life is not simple. The next few slides will be about the difficulties that are on the way. The root cause of almost all the difficulties there are is that, as said before, Android platform and our internal monorepo have different long histories. Now, the good part is that Sung, the build system for the majority of Android, was modeled after Bazel and was developed with full knowledge of Bazel structure. And the other good part is that Android's build does not need to be fully converted to Bazel to see benefits. The bad part is that even though Sung borrows some concepts from Bazel, it's just not quite the same, which makes the integration between the two tools hard. And there will be a long migration phase because we cannot just wave a magic wand to turn Sung into Bazel. What's even worse is that the migration to Sung has not been finished yet, and therefore, for a while, there are going to be 3 build systems in Android platform, that is to say, Sung, Make, and Bazel, which makes interoperability not so easy. Of course, there is a reason why Sung is different from Bazel, and that is mostly because the world of Android is also different than the world of the internal monorepo Bazel grew up in. The internal monorepo is a, monorepo, which means, among other things, that it's much more uniform. We have a uniform testing environment. We have a uniform environment to deploy to. Okay, not completely uniform, but clearly it's much simpler than the land of Android, where there are many, many different devices which all need to work. In addition to that, when one talks about Android platform, it's not really one code base. It's more like many different code bases. The biggest difference is that there is AOSP, which is a large part of Android, but not all of it. And there's the full Android source tree. But in addition to that, different partners Google works with, that is to say, companies who make chipsets or companies who make the actual devices, have their own code they add or remove to Android. And there is also the effort to build parts of Android separately, such that they can be deployed separately to the actual devices, that is to say, to do partial system updates, which is called Project Mainline. In order to be certain that a part of the operating system can be deployed separately, it also has to build separately, which is yet another way to slice and dice the source tree. Android also comes from a hardware background, unlike our monorepo, which comes from a software background, which is salient in a number of ways. For example, Android puts much more stress on integration testing, that is to say, uploading software to an actual piece of hardware and see if it works, and less emphasis on unit testing, that is to say, testing a small piece of code separately. This is the exact opposite what we have in our internal monorepo, where the rule is unit testing with a few integration tests sprinkled between. And of course, we have the biggest problem, which is the problem of every developer that has ever maintained a code base with a long life, which is legacy code. Now, in the background, you see COBOL. That we don't have, but those almost 2 decades of history have resulted in code that is sometimes not so easy to live with. So what's happening? There are 3 projects that are happening at the moment. The first is executing actions through Bazel. The second is doing the product configuration through Starlark, Bazel's configuration language. And the third is to run mixed builds with Swung, Bazel, and Kati. Kati is a term of art in Android land. It's a reimplementation of Make that was done a few years ago for performance. I would like to show the state of Android's builds before Bazel came around. I understand this graph is somewhat complicated, but the essence is that the build consists of 3 steps. First, what you see on the left is the product configuration part, where it is decided what exactly needs to be built. Its input is a bunch of make files that is processed by Kati, that is to say, the reimplementation of make Android has, which turns it into a set of configuration variables. These variables are ingested by Swung, Android's bespoke build tool, and another instance of Kati, which also take blueprint files and make files, that is to say, the configuration files of Swung and Kati respectively, and turn them into Ninja files, which are the description of the action graph, that is to say, the command lines that need to be run to do the build, and their input and output files. Then after this, a tool called Ninja takes the Ninja files and actually executes the builds. Where we want to be? Well, where we want to be is much simpler. We want to have build files, that is to say, the configuration files of Bazel, that describe both how to build things and what to build, have it ingested by Bazel, and have Bazel execute the resulting actions and output a system image. So what is the state of the affairs now? It's slightly more complicated because it's an intermediate phase. On this diagram, the green boxes are the pieces of code that are implemented for the migration. Firstly, for the product configuration, there are 2 new tools. One is to convert the make files to Starlark files with the extension BZL, that is to say, Bazel, and a tool to interpret those BZL files to emit the configuration variables that used to be emitted by Kati. Then, in addition to Swung and Kati, we have Bazel and build files, its config files, and a tool to convert the configuration files of Sung to build files. We call this tool BP to build, that is to say, blueprint to build. Currently, Bazel also emits Ninja files in order to facilitate two different ways of executing actions. The legacy mode with Ninja and the new mode with Bazel, which gives one access to all the goodies Bazel provides. These three work streams are in various states of completion. We are the further along with action execution. Bazel can run a full Android build as the action executor. What remains is to make sure that the action graph is well specified. That is to say, each action has its inputs and outputs declared properly, which is important for incremental builds, and to integrate Bazel's remote execution client into the build. Currently, there's a way to run builds remotely using a tool called ARI client, which is a command line tool that can be called either by Ninja or by Bazel. The second workstream, product configuration, is also seeing good progress. The make to Starla conversion tool has been implemented, and there are no known bugs in it. And there is good progress on integrating it into the actual build. What remains is actually converting the make files to .bzl files and checking them into the source tree. The largest challenges there are in the third workstream, that is to say, integrating Bazel into a build with Sung and Kati, because that's when there needs to be a conceptual mapping between the concepts on these three build systems. And it turns out that all three have a complicated conceptual model that needs to be reconciled somehow. Current work is being done on finding a mapping between the concepts of Sung and Bazel. Kati, not so much, because the world of Kati is much simpler. And there is progress on implementing an automatic conversion tool. Checking in build files instead of blueprint files haven't been started yet. We'll start once there's enough confidence about the fidelity of said conversion tool. I would like to talk about action execution, that is to say, using Bazel as a better ninja. This was work that was much easier than expected, mostly because the interface to action execution is pretty narrow. An action, after all, is a very simple thing. It has input files, output files, and a command line that one needs to execute. The work required some design compromises in Bazel, but nothing too serious. And it actually worked while requiring only very small changes to Android platform, mostly to specify a missing input or output here and there. This is not default yet, but I'm very confident that Bazel can actually work as an action executor, and it provides a bunch of benefits already. One can use Bazel's remote execution engine, one can use Bazel's action sandbox, one can use Bazel to query the action graph of the build, and Bazel also provides change pruning, that is to say, the ability not to re-execute an action when its upstream actions have been executed but did not change their output files. For example, when you add a comment to a C++ source file, then the compile is re-executed, but the object file it emits is not changed. Therefore, you don't need to actually rerun the linker. The product configuration is a more interesting part because it's unique to Android. It's a part of Android that is not touched very frequently, and therefore there is not a lot of knowledge spread about it at Google and at partners. It's a way to describe in a modular fashion what exactly needs to be part of a system image, and it's built on the 1976 vintage make build tool. The idea is to say things like, I want to build this device, and this device should have an AOSP image, but with this Android app in addition, and with a few parts removed. Since it's built on top of make, there isn't a lot of error checking in there, and it's not very well tested. But on the flip side, the make files describing the product configuration are well structured and kind of easy to understand what they want to do, which is to our advantage because it makes it easy to build a parser. Actually, I'm saying parser, but sometimes one doesn't actually need to parse make. one can only use a text-based method to understand them and to turn them into Starlark files. Here's an example of how a make file looks like. That is to say, this product should be like cuttlefish with a package called craftsvm in addition, and so on. And here is how the same concept would look like when described in Starlark. The last thing I would like to talk about is mixed mode builds, that is to say, making Sung and Bazel, and to a lesser degree Kati, interoperate with each other. The end result of this system will be a tool to convert the configuration files of Sung, that is to say blueprint files, into those of Bazel, that is to say Bazel files. We wanted this tool to be mostly automatic because that's the only way we can migrate the code at scale. It will probably not happen. It will probably need some manual help because both Sung and Bazel have rich conceptual models, and there is no point in implementing an automatic mechanism for migrating things that is used just once or twice in the code base. But we do want the overwhelming majority of the migration to be automatic. The reason why this is difficult is that because Sung and Bazel are extensible in different ways. Sung is extensible in Go, which means that extensions can use the full power of Go. And Bazel is extensible in Starlark, which is a very limited programming language with a very limited API. We want to migrate code that can do more to a system that can do less. Now, Starlark has these limitations for a very good reason. This is what provides opportunities for Bazel to do sophisticated ways of caching, but it's a difficulty. The other difficulty we are facing is that we don't want to make the lives of people who work with Android harder, not even temporarily, which means that we have to be careful to slot Bazel into the build process in such a way that it doesn't make builds slower or less comprehensible. Admittedly, this is difficult. So what is it that has already been accomplished? On Bionic, there's good progress. We can build Bionic in such a way that is bit by bit the same as the build done without Bazel. What remains, however, is building Bionic in all the various ways in which it's built within the build. For example, it's built with various sanitizers, ASAN, UBSAN, and so on and so forth. It's built so as to provide an interface for various Android API levels, such that it can be linked against by applications requiring those various API levels. All this remains. Executing the actions comprising the build with Bazel is mostly risk-free. The Pixel 3 system image can be built with Bazel without problems, which means that I'm pretty confident that everything else can be too, but it's Pixel 3 we tested it with. And now one can start adding edges to the action graph to make it fully declared and incremental. I also consider product configuration a solved problem. It's not integrated yet into the build, but the translator is already operational, and there are no known bugs on a full build, which means that there are probably no serious bugs that remain. So it appears that most of the risk in the past. There is still some risk left, and I think that a large part of that risk will be gone by the time we can build Bionic in all the ways that it needs to be built during a full build. But all in all, I'm happy with the progress so far. On to the future. Thank you for listening to this talk, and I hope you will follow further developments on this project.
Thank you, Lukasz. Bazel for Android Platform is an ambitious project that will have lots of great impact on Android platform developers, their workflow, and build and test times. Next, we'll hear from Alex Eagle on that one API to help accelerate your migration to Bazel. Take it away.
Hi, everyone. I'm so excited to be with you today. My name is Alex Eagle. I'm the author and one of the co-maintainers for Rules Node.js. Also recently became a maintainer for Rules Python. Formerly, I was at Google on the Angular team, and I was one of the team that rolled out TypeScript language into Blaze, Google's internal version of Bazel. And now I'm working to migrate enterprises to Bazel. Before I start, I just want to say how much I miss interacting with all of you at BazelCon in the hallway track, like we did the last 3 years, and I hope we get to do that again soon. So my talk today is about migrations and how to make them easier for your business. And as we observed last year in my talk with Greg McGowan at BazelCon, Bazel migrations have a lot of risks. So you might introduce a bug because you made a change in the build system. It can certainly take longer than you thought. It can cause problems for your developers. And in our talk, we went over ways to mitigate risks. And today I want to dive deeply into one of those, which is only change one thing at a time. The reason we do that is that it's much easier if something breaks, then we know what caused it, and we can keep things simple, and it's easier to reduce that breakage down to one precise cause. But what we often find is that it's hard to avoid being forced to change something in your build. You may find that there's some existing part of your legacy build system that just doesn't seem to work with Bazel. And in my experience, there's one API that we can learn that helps us to avoid having to make those kinds of changes in the tools that we call. And that API is simply the process. You're probably used to seeing processes on your machine. You may not think about them that much. But there is actually an API here. It's available everywhere. And this is how Bazel interacts with the tools that you're running. So if you can think in terms of this process API, I think that helps you to adapt Bazel and the way that you're calling your tools, rather than having to change the tools that you run. So briefly, let's just remind ourselves what a process is. This is how programs are run on your computer. Every tool that you're running today in your build, in your legacy build, is running inside of a process. A process works everywhere in every language, has great support for interacting with processes, and it works on Unix type systems, including Mac. And also everything I'm going to talk about is almost translatable to Windows. And so I think this is a great general purpose way to think about the problem. The one slide I want you to remember from this talk is that you may hear someone say, that tool doesn't work with Bazel. And this should be the sign to you, this is a trigger. And you say, why not? Is that really true? I find that it's often not true. The main reason you can tell that you can challenge that statement is to simply ask, how can the tool tell that it was called by Bazel? How was it called before in the legacy build system? And if we can figure out all the parts of this process API and make everything look the same way it did when the tool was called under the old build system, then it should work exactly the same way. So in this talk, I'll give some practical workarounds for some scenarios that we ran into while we were developing Rules Node.js and applying them at companies. But I do want to call out that this is not all, there are trade-offs being made here. In some cases, in order to make your tools work, you're going to give up some of Bazel's goodness in some part of your build graph. So we're going to trade off compatibility for optimizations. This is something you have to think about in the context of your migration. It might make sense to have these sort of de-optimizations at the beginning in order to get everything working the same way. And then you can find the slowest parts of your build and then just evolve those subparts of the graph. So one example of a trade-off is that the Swift compiler can be much, much slower by orders of magnitude if it doesn't find the incrementality bits from its previous run. And so if we think about simply running the Swift compiler as just some arbitrary process, then it may be a lot slower. That's the kind of trade-off that we may need to make. So let's just look at one example of how Bazel calls a tool. I'm using genrule here because I love genrule. But really, anytime Bazel calls a tool, you can think of it this way. It may just be that if you're using a custom rule, you don't see the tool spelled out like it is here, and you don't see the command line that it's calling. But if you unwrap the implementation of a rule, you'll always find somewhere that it's calling something like context.action.run and calling out to a tool in this way. So for this example, the tool is YQ. This is a variant of JQ, the popular JSON manipulation library application, and it handles YAML files. And so this one is just converting YAML to JSON. And it happens here. You can see that the command line has some flags that we're passing to this tool. And those are sufficient in this case to make the tool work the way you expect under Bazel to read inputs and produce outputs. So this example is fine, but we're going to go through the rest of this talk with imagining that we're running a tool where this is not the case and something is not possible to run. So one option for how to change the way the program is called is to find some way to change the behavior of the existing runtime. So this is a little hacky, but one example under Node is that there's a flag -- require that lets you run some bit of arbitrary script right before the program starts. Another example is in Java, you can pass the class path argument to the JVM, which allows you to do something like maybe shadow an existing class to change its behavior. This is obviously risky because it's easy for monkey patching to cause weird action at a distance bugs in the program. So be really careful doing this option. Do like a single one-liner. I'll show an example of this later. Another option is to change the entry point of the program, but staying within the same process. So essentially you take that tool and instead of calling it as a process, you call it as a library. You find wherever that CLI entry point is, and as close as possible, try to invoke it the same way. And that gives you just a little bit of room to swap in your own logic at the top of the program to change the way it runs. This is nice because it allows you to have more power inside of that same process. You can do things like mutate the arguments, and that would be harder to do in the third option, which is the most common option, where you'll just run some extra program as a parent process. This is typically something like a bash script, and it just does some sort of tweaks to the way the process is being run, and then it invokes the original tool as a child process. For the rest of the talk, I'm going to dive into the specifics of the process API and how to use one of those 3 wrapper approaches to make the execution match the way it ran under your legacy build. So the first things I'll group as roughly the inputs to the process. So it takes a list of arguments. Obviously here you must take a lot of care with things like spaces and escaping so that the arguments are preserved exactly when Bazel calls the program. It can read a dictionary of key value pairs from the environment. It can run in a working directory, and usually most of the paths that the tool are going to work with are relative to that working directory. And it reads bytes from its standard input. So let's dive into a few of those. I'm just going to give a few examples here. This is not meant to be an exhaustive list, but this is sort of how in Rules Node.js we've thought about using this process API to fix some of the compatibility issues. So when dealing with arguments, for example, you might find that your wrapper needs some of its own arguments. So if you're in process, you can just mutate the argv, just strip some things off of it, assuming that your language runtime has a mutable version of the argv. Or in a parent process, you can just take some of the arguments yourself and then selectively forward some of them onto the child process. So one example we've had is a test runner where we needed to pass some Bazel arguments to the test runner, but then the user might want to pass their own args to their tests, and we need to keep those 2 things separate and make sure that the test runner doesn't see the arguments that are meant for Bazel to control the program. The next example is environment variables. So this is a little confusing, and I'm going to have to point you to the Bazel documentation. You should look up the use default shell env argument, which changes the behavior of a given tool so that it uses the action environment around it. And then you can use --action env to change the environment for all of the actions that run. So, and keep in mind when you're changing the environment for an action that this will be part of the action's input hash, and so it will bust the cache when it changes. For things that are runnable like tests, there's the --test env, which doesn't have as many caveats and generally works fine. Then you also have a few rules that have an env attribute. So this is a really nice, easy way to pass some additional environment variables, but it's not typically on most Bazel rules that I've seen. And of course, as a last resort, you can imagine if you write a wrapper, then you can just take an input file, which expresses all of the environment variables, and then you can just set those either in process or in a parent process wrapper so that they're available when the tool runs. The next one I'll talk about is the working directory. We have a couple different examples here. So the first is that, of course, Bazel always runs tools in the workspace root. And this is usually different from how most tools expect to be run. Especially in the JavaScript ecosystem, tools tend to expect that the configuration file is going to be in the same directory as the working directory. So again, here we can wrap the program with a parent process that changes the working directory and then spawns the original as a subprocess. Or we can do it in process. So in Node, I mentioned there's this --require option. So here's an example where we take --node options, which is a way to wrap the arguments. So we're going to strip that off in Bazel. And then the --require part is going to get passed to Node. And then the argument to that is a little JavaScript file that's a one-liner that just does stderr. And so this is a cute way that we can change the working directory of a process without having to make a wrapper around it. Keeping in mind that wrappers have that extra expense of having an extra process and possibly an extra dependency on something like bash. So this can be a nice minimal way to do it if you need it to run everywhere. I'm not sure if other language runtimes have a feature like this, but it's worth looking for. The next example is where the working directory needs to be in the output tree. So this may seem strange, but there are actually tools in the React ecosystem, for example, where the output always goes into /build and it's not controllable by the user. So to make this tool work under Bazel, you're going to have to switch directories to the output tree and then run the tool. And then the outputs that it writes will just happen to match up with where Bazel expects them to be written, and it will work. The next section is about the output parts of the process API. So this is the exit code, which is just generally saying whether things went okay when the program ran, and the standard out and standard error, which are 2 byte streams that the program can write to. So for the exit code, most tools will just exit 0 on success, and Bazel fails if they exit non-zero, and that's typically what you want. There are some cases where the exit code actually does matter. So one of them is if the tool exits with some other novel exit code, like how many changes it made, because the programmer felt like they were being clever and they were allowed to return whatever exit code they wanted, so they added some information in there. The more common example we've seen is that we want to write a test under Bazel that's a negative test. It asserts that the build fails with some error message. And this can be important in your migration. You want to have a way to express that as you're writing the Bazel wrappers for your code, that you want to know that the error handling case is going to work correctly. You want to write a test for that. So one way to do this is to write a parent process wrapper that captures the exit code. Another way under rules Node.js is actually Matt McKay, one of our co-maintainers, added a feature so you can just request that the exit code be one of the outputs rather than being seen by Bazel. So it will always exit 0, and you can reference the exit code as an output file. Standard out and standard error are very similar. Again, there can be things that a tool wants to produce on standard out, and you want to grab those as an action output. So you can use general for this, as we showed with the YQ example earlier. Or you can use a parent process wrapper that can just read from standard out and convert it to being an output file. And again, Matt McKay built this into rules Node.js. So in our case, you can just ask for the standard out to be an action output file. The other obvious caveat here, if you've done anything with persistent workers or with iBazel, which is the watch mode for Bazel, those both expect to communicate with the tool over standard in and standard out. And so you may need to patch the runtime in some way to assign standard out to standard error. In both cases, you're free to write to standard error, but you don't want to have to go through this whole tool and figure out all the places that it writes to standard out and change them. So usually you'll find some way in your runtime to be able to patch that behavior. The last category of API I want to talk about is interactions outside of the process. So there are parent and child processes that can know about each other. And there's obviously the program can write to the file system and read from the file system and has open file handles called descriptors. And also it can receive signals telling it what to do. So for the first of those, there's this concept of a union file system under Bazel. So Bazel is very opinionated about putting the outputs into this distinct tree, Bazel out, and not next to the source files. But a lot of tools expect to be able to make relative references between a generated file and another source file. So I call this union FS because our solution for this has typically been to convince the program that those things are actually next to each other or change the way that these relative references work. But that again is an example of needing to make significant changes to the tool instead of just making it compatible under Bazel. So this one is a cool trick. You may think that Bazel disallows you from having the same file be in the input tree and the output tree. But this is actually only true if the output is labeled, which is to say it was a pre-declared output of some rule. As long as you just reference a target and that target does some copies and it happens to put copies of your files into the output tree, Bazel doesn't know about that and it works fine. So you can just copy your sources to the output tree and make it self-contained, and then your tool will run and see the files next to each other like they were intended to be. We actually have this built into rules Node.js. So you can see here's a documentation link to our copy to bin rule. And if you feel like this would be useful for you outside of Node.js, which I imagine it would be, you can find this pull request number 217 on Bazel Skylib and comment there. They're actually asking whether it's useful generally outside of the Node.js use case. Let's talk about signals for a minute. Signals are an interesting way to affect the process's behavior. Normally under Bazel, you don't think about signals being part of the API when you call a tool. But if you're writing a parent process, then this can be a really clever way to control the child process. So let's take, for example, watch mode. So watch mode is where a tool expects that it's going to watch the source files or something in the output tree, and then it's going to rebuild them every time it changes. So this can be a problem because the intermediate state in the Bazel out folder is it's disruptive. The Bazel will actually unlink the files, meaning like they appear to be deleted and then re-added. And so tools can freak out, and they can also see intermediate state where not all of the things have been written to the output tree yet. So I want to give credit to Dan Muller from the Rules Node.js team who came up with this approach for running watch mode tools. What we can do is, instead of having to make the tool aware of the Bazel persistent worker API or the iBazel API, which write to standard in and tell the tool that it's time to work, we can actually intercept that part of the communication with Bazel. So intercept standard in and write to standard out to communicate with Bazel from our wrapper process. And then the wrapper can control the child process by sending it a sig stop to pause it and a sig continue to resume. This is the same thing as if you press Control Z on the command line and then FG to resume the program. So this is really cool. It just pauses the program while Bazel is running so that you can get that same watch mode behavior without having to change the program you're calling. Symlinks are a common source of trouble, especially in the JavaScript ecosystem, because Bazel runs tools in a symlink forest. If it's an action, this is called the exec root, and if it's a test, it's called the run files root. And under the default spawn strategy, there's a bunch of symlinks here out to the rest of the file system. And if the tool follows those symlinks, then they can find inputs that they weren't supposed to read. That makes your build non-hermetic, but it also can make the tool behave wrong because it may find some input that conflicts with some input that you wanted it to find. One tip here is to go check out the Sandbox FS, which was this effort by Julio and some others to make a better sandbox. It doesn't just based on symlinks. I don't know what the state of that project is. You might be able to configure your tool to avoid following symlinks. In Node, it's pretty typical that you can pass a couple of options to the Node interpreter. And actually in Rules Node.js, we went so far as to have a patch written by Ryan Day, which changes the file system API so that the symlinks actually appear to be regular files and directories rather than symlinks. So the program can't tell it's running in this Bazel environment. The last thing I'll mention is sometimes you can just back off from the sort of Bazel idioms. So one idiom is to run things in a sandbox, but Bazel makes input files read-only. And if your tool expects that it's going to write to the input files, you may have to just give up on sandboxing. You can always mark this as local, and you can find a way to make that tool run. Again, this is a trade-off between the Bazel idioms and making things more compatible. So those are all the examples I have time for today. I just want to remind you that I think in a migration, it's wise to try to change only one thing at a time. And you should always challenge the notion of this tool doesn't work under Bazel to find a way to run your tools the same way you did before. Thanks so much for watching.
Thanks, Alex. I love that you brought your experience from working with Rules Node.js to be able to help the community with their migration to Bazel. Next, we'll hear from Yun Peng and Oleg Voinar about Debian Ubuntu packaging for Bazel. Take it away, Yun and Oleg.
Hello, thanks for joining this talk on Debian packaging for Bazel. I'm Yun. I work on the Bazel team from the Google Munich office.
And I'm Oleg. I am a Debian developer and the lead for the Debian packaging effort for Bazel.
In this session, we want to talk about how we manage to package Bazel for the Debian distribution. First, we'll show you what situation led to our collaboration. Then we'll talk about how we overcame some of the challenges we've had from both the Bazel side and the Debian side. Last, we'll see what's the outcome of this joint effort so far and what's the remaining work. Oleg will start with some background of this effort.
Thanks, Yun. So this all started when I joined the Debian Med team in spring of 2020 because of their efforts to package software that could help experts fighting COVID-19. One of their highest priority packages was TensorFlow. However, that package was also marked as extraordinarily difficult. At this time, Bazel was not available in Debian, therefore previous packaging efforts had unsuccessfully attempted to implement a custom build system. The solution was obvious to me. Package Bazel for Debian, how hard could it be? Unfortunately, neither the Debian team nor the Bazel team individually possessed all of the required expertise to make that happen. Therefore, we rapidly put together an effort to leverage each team's unique abilities to achieve this goal. Now, the primary goal was simple: introduce Bazel into Debian so that it could be used to build TensorFlow. Because of the pandemic implications, we wanted to proceed as quickly as possible. Therefore, we agreed that we were willing to accept temporary workarounds if it helped us to achieve our goal faster. We didn't know exactly how long this effort would take, but we wanted to finish within a couple months. However, the previous packaging effort had lasted 5 years and had ultimately been unsuccessful. That was a sobering reality. Yun will now tell you more about our collaboration on this project.
So the Debian team first reached out to the Bazel team on GitHub. We soon had a video conference in April 2020. A task force was set up with me being the contact point from the Bazel team and Oleg from the Debian team. In the first few weeks, we had frequent email exchanges and video meetings to understand what problems we had to solve. And finally, we came up with a viable work plan. So what challenges do we have to overcome exactly? I'll first talk from the Bazel side. To comply with the Debian policy for packaging software, we had to bootstrap and build Bazel without any bundled dependencies in source or any downloaded dependencies from the internet. Also, we had to install Bazel following Debian standards. I'll talk more in the detail. Bazel bundles some of its dependencies as source code and jar files under the third-party directory. In the Debian build, those dependencies should be replaced with their corresponding Debian packages, which are installed on the system. So, for example, JSON 2.8 is checked in Bazel source and used by a Java import rule. So how did we make use of the JSON jar installed via the Debian package? First, we created a new local repository rule pointing to user shared Java, because that's where all Java libraries are installed. We named this repo as Debian Java Deps. Of course, we had to write a build file for this repo so that Bazel knows what targets are available. Here we write a Java import rule for the JSON. Note that the name of this target is exactly the same as the one in the third-party directory. To be able to replace the original JSON target with the one in the local repository Debian Java Deps, we wrote a macro for the Java import rule called distrib Java import. It is essentially an alias rule with a select statement. By default, it delegates to a native Java import rule that uses the checked-in jar file. We use an attribute called enable distributions to indicate what distributions are supported. If Debian is in the list of enabled distributions, it means there is a target in the Debian Java Deps repo with the same name that can replace the original target. Then a condition of the Debian build for this target is added. So when the config setting for the Debian build is matched, it redirects the target to the one in the Debian Java Deps repo. We also created similar local repositories and wrote similar macros for CC library, CC binary, so that dependencies like zlib or the Portal-C compiler can also be replaced. So with not so intrusive changes in Bazel's build file, we added the ability to build Bazel with libraries installed on the system, which can be enabled by the --define distribution equal Debian flag. And we can safely strip out the bundled dependencies in Bazel's Debian source package. Note that this approach can be easily extended for other Linux distributions as needed. The other part of Bazel's dependencies come from the workspace file, which needs to be downloaded at the build time. For example, we have Bazel skylib, rules Java, etc. Obviously, they are not packaged for Debian by the time we were trying to package Bazel, but they are used in many build files, so we cannot simply remove them. To work around this, we had to write a patch file to create mock repositories, which contain the build files and the BZL files required. Then, with the override repository flag, we can tell Bazel not to download those dependencies, but to use a given directory for a certain repo. I admit this is kind of a hack, but in order to get Bazel packaged as soon as possible, this is still acceptable. The last challenge is about installing Bazel. Bazel is implemented in the client-server architecture. Users usually download Bazel as a single binary, which is in fact a self-extracting archive. The first time you run Bazel, it extracts itself to an install base somewhere under your home directory, which contains the Bazel server and the embedded tools. Then the binary itself serves as the client. However, this behavior is not allowed in Debian. The user bin Bazel binary must be stripped while creating the Debian package. So it will only be the Bazel client and will not contain any additional data. Therefore, we actually had to create the whole Bazel install base in the Debian package. So on the left side, it is a normal install base for Bazel. On the right side, it is an install base in Debian, which is under user share Bazel. However, the C++ binaries should be installed in certain directories because they are architecture dependent. So we use Symlinks to reconstruct the complete directory structure for the install base. And finally, with a global Bazel RC file, we can tell the Bazel client where the install base is, so that users can just invoke Bazel as normal. So that's the major challenges from the Bazel side. Next, Oleg will tell you more from the Debian side.
Thank you, Yun. I'd like to highlight the challenges for both teams were discussed and addressed together, no matter which team took the lead on the solution. And the up-to-date flexible work plan that Yun mentioned earlier was critical in keeping our efforts synchronized. Also, having a common understanding of our mutual desired end states and constraints made things much easier when the plan inevitably changed. Regarding some specific challenges that the Debian team took the lead on, we found that we had significantly more dependencies than we had expected. Each of these dependencies had to be packaged for Debian before we could package Bazel. Now, the Bazel team was very helpful in determining which were absolutely needed and which could be worked around. Some of these dependencies were fairly trivial, and some were not. On the difficult side, some dependencies needed to be built with Gradle, which is not very well supported in Debian, to say the least. Also, the gRPC Java and OpenCensus circular dependency caused quite a few headaches. Our second challenge was that Debian contributors are all volunteers. We had to plan for extra time as both packagers and supporting Debian contributors often have rapidly changing time budgets. For example, even once we had completed our initial packaging effort, we had to allow significant time for Debian's quality control team to review the packaging, and more importantly, to review the licensing. Now, licensing issues are critical for distribution. We wanted to identify anything that could present a problem for Debian distributing the software. For example, we discovered a JSON license in the Bazel source that we had to investigate since it could not be included in Debian. We also had to clarify some licensing issues that our quality control team caught related to Checker Framework, which is one of the Bazel dependencies that we needed to package. This effort quickly grew beyond the Debian Med team that originally spawned it, and now it has its own team in Debian. While the scope of the Debian Bazel team's efforts has grown, the core purpose of the team is still the same as in our original project. That is, to enable TensorFlow and pandemic-related packages in Debian. After almost exactly 6 months, the Bazel Bootstrap package was in the Debian repositories. It is scheduled to release with Debian 11 later this year and with Ubuntu 21.04 in April. Now, this is a great time to point out that Bazel has a capability to bootstrap itself from source. That is a killer feature, and that is the variant that we packaged initially in Debian because it was the easiest to start with. I can't imagine how difficult this process would have been to implement if we had to request permission to start with a pre-built Bazel binary in Debian. Now, our TensorFlow packaging is ongoing, and we're working with that packaging team to help with any workarounds that they may need to help accelerate their packaging efforts. Most importantly, we have developed a solid relationship between the Bazel and the Debian teams, and that relationship is continuing to bear fruit as we tackle new challenges. And you saw some benefits upstream as well, correct?
Yeah. Besides the impact we had in Debian, this effort also directly benefited the Bazel project itself. First, we had our dependencies polished. We deleted unused dependencies, upgraded outdated ones, and as mentioned before, we also fixed some problematic license issues. Besides, the solution we developed for packaging Bazel for Debian can also be extended for other Linux distributions. Therefore, the Bazel project became more distribution friendly. Next, Oleg and I will talk about the remaining work.
Yes, now we are targeting Debian 12 and Ubuntu 22.04 for our next steps. We've already started the first part of that plan, which is to remove the hacks and the workarounds which we initially implemented for expediency. A key part of that is to properly package additional elements of the Bazel infrastructure, such as Java tools, Java rules, CC rules, and others. Currently, we have Bazel platforms and Bazel Skylib packaged and awaiting the start of the Debian 12 development cycle. We are planning to add the others in the coming months. We also want to enable DebHelper to natively support Bazel builds. DebHelper is the tool that we use in Debian to make upstream software into Debian packages. In contrast to the workarounds that we're using for TensorFlow, we want DebHelper to automatically detect that software is using Bazel to build. DebHelper will then be able to call Bazel to build that software, find the resulting built files, and install them properly into a Debian package. This will be further facilitated by some ongoing efforts in Bazel that Yoon will share with you.
As you may have noticed, the issues of building a project offline with system-installed libraries are not unique to the Bazel project itself, but also apply to other projects that are built with Bazel. This is one of the pain points of how Bazel currently deals with external dependencies, and solving this will be very helpful for the effort to integrate Bazel with DebHelper. Improving the dependency management in Bazel is an ongoing effort and also a priority of the Bazel Open Source team this year. That's all for this talk. Thank you all for joining us at Google Open Source Live. I would like to especially thank Oleg and other Debian developers for initiating this effort and driving it forward.
And I would like to thank Yoon and the rest of the Bazel team for all of their support in helping us to complete this very ambitious project. Thank you all for joining us.
Thank you, Yoon and Oleg. I want to thank you both for your work making it easier for COVID-19 researchers to use both Bazel and TensorFlow to find new and better treatments for COVID and other diseases. I know that it was a team effort over some months, but I really appreciate your leadership and the positive impact you're having on making the world a better place. Okay, with that, it's a wrap, and now it's time for the after party. Come join us at the after party by clicking the Watch Live button on the event's agenda page to be redirected to Google Meet. Anything else, Joe?
Well, today's speakers will also be joining the after party, and we'll have some quizzes, interactive activities, and surprise guests. We hope to see you all there. Thanks.